In our next segment, we're going to be discussing Gauss's law. And Gauss's law is going to allow us to use electric flux in order to establish the electric field strength for different distributions of charges. So we're going to work in this first part of this video by putting a spherical charge inside of what we're going to call a spherical Gaussian surface. So you can see here sort of a representation of, you can imagine a charge at the very center of the sphere I have here, and you can imagine the field lines coming in or out due to that spherical charge inside of the spherical shell. And I like to give you guys these visual representations like this because on the board I'm forced to draw in 2D, but here you can sort of see this 3D where we're going to need to integrate over the entire enclosed surface, not just work with the two-dimensional circle. Alright, so as I said earlier, we're going to have a spherical charge inside of a spherical shell. So the spherical shell we're going to refer to as a spherical Gaussian surface. So this matches up with Gauss's law, where we're going to define the area that the electric flux is going to be going through very strategically. Because our goal here is to have it so that the field lines are either completely parallel or completely perpendicular so that we don't have to actually break anything into components. This is going to allow us throughout this course to avoid having to put things in spherical or cylindrical coordinates in order to do an integration. Here we're going to make use of areas that we already know the formulas for and set up a matching charge. So the charge and the Gaussian surface should match up shape-wise so that your field lines are always perpendicular or always completely parallel. So we're going to go through different shapes as we progress through the rest of this chapter. For now, we're going to work with a spherical charge inside of a spherical shell, and I'm kind of drawing these green lines to show that at that particular point the surface is actually perpendicular, sort of the same concept of, even though we're on a spherical Earth, we assume the surface is flat. We can't really see that spherical shape because it's much larger than our perspective. So I'm going to write down the electric field equation for a spherical charge, so a point charge. I have rewritten the Coulomb constant as 1 over 4 pi times the electric constant. So the electric constant is epsilon naught, and epsilon naught is equal to 8.854 times 10 to the minus 12 Coulomb squared per Newton meter squared. And we're going to be using this form of the Coulomb constant throughout this particular topic in order to allow us to sort of work better with the 4 pi out front. So we just learned electric flux is equal to electric field times the area. I've removed the dot product because we've set this condition up so that the electric field and normal to the surface are taken care of. So our angle in this particular case would be 0. Alright, so I plugged in our equation from above for the electric field, and the surface area of a sphere is 4 pi r squared. So the 4 pi's cancel out, the r squares cancel out, and you're left with the charge divided by the electric constant. And I could have done this distribution with any set of charge and Gaussian surface, but this is just the easiest because the 4 pi naturally and the r squared naturally comes out of the surface area of a sphere, so it makes the derivation a lot easier. So we get the Gauss's law is the idea that the electric flux is equal to the surface integral of the electric field dotted with the surface area, and that's equal to Q enclosed divided by the electric constant. So this electric flux is going to depend only on the net charge inside of the Gaussian surface. So not outside, only inside. And we're going to be making use of this as we progress this particular topic, not to calculate the electric flux, but in order to use this half of Gauss's law. So we're going to solve for the electric field. So we're going to derive the equation based upon the distribution of charge and then use that equation to solve for the electric field strength. So a side note here that I want to point out here is that sometimes we represent charge in a slightly different manner. So we might do it charge per, whether it's length or area or volume, depending upon what the charge distribution is. So you might see lambda here meaning linear charge density, so that's charge per length. Sigma here representing surface charge density, which is charge per area. and then rho here representing volume charge density, which is charge per volume. So sometimes rather than giving you the charge and the length separately, we'll give you the charge and the length as a ratio of each other, so that you're going to essentially replace two variables with one number.